Remember when we talked about we had an annual growth rate for our CD, our certificate of deposit, and but it was split up into 12 months? When we looked at, okay, let's divide that rate into 12 months and do it 12 times. Well, that let's look at kind of how things grow at different divisions. So all of these values over here, this is looking at the growth of a $1 investment. Just to make it a little easier to see, $1 investment after 1 year with 100% interest. So if we have 100% interest, again, all of these are 100% interest, which is great. So if it only compounds once, then we get the true doubling. But if we do 50% interest twice, which is really what's happening here, right? Semi-annually, 100%, we divide it into two pieces, 50% after 6 months and another 50% after 6 months. So it actually is growing even more. If we split it into quarters, right, 25% interest, 4 times, and again, all of these are still 100% annual interest. It's just how often is that interest being applied? Notice that it's growing by even more. Monthly, we're splitting it up into 12 pieces. Daily, splitting up into 365 pieces. Hourly, I don't know. Minute, I know that because of rent. It's like 525,600 minutes or something. Um, Notice what's happening. The more frequently we compound, even if we have the same annual interest rate, the more frequently we compound as we go down, the more money we're going to have. But what's happening with these numbers? They're getting really close to something, right? The difference between these few is kind of big. The difference between these three is almost the same number. What number is it getting close to? Dun da da da! Fanfare time. This is a very special number called Euler's number. And it looks weird to say number E, but it's a number just like pi, an irrational number. It goes on forever. 2.71828, blah, 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 blah. So it's a very special number that we're approaching. And we use this number to model continuous growth. It's also very useful in calculus. So if it's not growing every day, but it's growing continuously, every moment, it's different than the moment before. But again, the more often something grows, the less it's going to grow at any given moment. So we model that with continuous growth. And that uses this E. Your calculator will have an E button on it, probably close to the pi button. Desmos, you can just type in E. There you go. It tells you that that's a number. So we're going to be using E a little bit here and more in calculus for continuous growth. So another way of writing exponential functions, instead of just AB to the X, or A times 1 plus R to the X, is like this. A, basically the same A, E to the RX. And R is the continuous growth rate as a decimal. And A is a starting value. So the A and the R mean the same things. That's nice. Okay. And this is used when quantities change more continuously, like chemical reactions, growths of very large populations. Small populations don't grow this way because, well, you either have one person or two people, not fractional people. And it's also very useful in calculus. Let's get some practice and then we'll move on. This won't be used a ton. E won't be used a ton in this class, but I want to cover it, so we'll have it later. So if we have $1,000 invested in a CD, this is seeming a little similar to before, earning 1.2% interest compounded continuously, how much would we have after 12 years? Remember when it was compounded every month, we looked at 1 plus 0.012 split up into 12 months. We had to do it 12 times. Well, continuous would be like if this were an infinity, which is kind of weird. So we're not going to write it like that anymore. Split it up into infinitely many pieces. That comes from the idea of a limit, which is a calculus topic we'll talk about next quarter. But anyway, we're going to use this y equals ae to the RT, just like was mentioned right here for continuous growth. Well, then it's not too bad. A is just the starting value, like we had before. R is the interest rate as a decimal, 0.012, as before. And T, or X, is going to be how many years? So before we found it after 24 months, we found it was like going to be $1,024. What happens if it can, the same amount of time, 2 years, but compounded continuously? Well, let's plug in 2. And let's see what we get. Good practice trying to type this in your own calculator as well. 1,000 times e raised to the r times t, which is 2. That's still $1,024. $1,024.29. How does that compare from our answer before? I'm pretty sure the one before was $1,024 too. Where was it? Oh, before it was only 28 cents. So if you get the choice, do you want it compounded monthly? Do you want it compounded continuously? You get more money with the continuous. You get an extra cent after 2 years. And again, that has to do with what we talked about in this table. The more often something compounds, the better you're going to be on average. And the difference between annual and monthly is big. The difference between monthly and continuous is much less big. All right. So there we go. That's the answer to the question. And then we compared it. It's just 1 cent higher. The difference would be bigger if we did more than 2 years. But for 2 years, it's not that different. All right, that's it for this video. The next video, I do some homework problems if you want some extra practice. So stay tuned. Otherwise, good luck.